Okay, so after rivets, we're going to talk about welding. So, welding is a term generally applied to simultaneously melting together of two adjoining items. So, steel piece to a steel piece or an aluminium piece to an aluminium piece. Perhaps it's not evident, but generally they have to be the same sort of stuff. Yes, you can weld mild steel to stainless steel, but you're not going to end up with a stainless weld. Aluminium to aluminium is still aluminium, although different aluminiums weld differently, etc. The heat you use to melt the metal doesn't need to be an electric arc. That's what we commonly see, but it can also be an oxyacetylene torch. There are other ways, such as thermit welds, but also friction and forge welding, which I'll just touch on. They're not the ones you'll see most often, but it's just useful to sort of know they exist. The other thing is there are impacts on material properties in what's called the heat affected zone. So whenever you weld a piece of metal, you obviously get it hot enough to melt it. Well, that melting obviously causes all sorts of disruption to the structure of the metal in that localized area. So depending upon the application, you may need to preheat, you may need to post-heat, you may need to retemper once you finish making your welds. And it just depends, and having a little bit of knowledge and thought about this before you start is obviously useful. I just want to make a quick comment here, because whilst we're going to focus on welding, there is also this process called brazing. And brazing is joining of two bits of metal without melting the parent metal. Now, as far as I know, soldering is something you've all done in MEC 2110. So that's a form of a low temperature brazing. If you're talking about copper pipes in a house for plumbing, today you would silver solder those. Years and years ago, you would use a soft solder or a lead-based solder. Now that's a lead tin alloy that you're joining copper pipes with. The common term when most people talk about brazing, they'll think about a bronze metal. And if you walk around Bunnings, you'll see brazing rods with a blue flux on the outside of them, which is just a general purpose bronze weld or bronze brazing rod. That is normally used for joining pieces of steel together, and it sort of wets the surface with bronze material, and the bronze flows into the joint. It is not a second-class operation. It still performs a very, very strong joint. It doesn't upset the material properties as badly as welding. And in fact, a lot of space-framed race cars, Formula One level race cars, were all nickel bronze welded for a very long time before obviously they've moved on to other technologies. So a little bit about the different types of welding. Oxy welding is basically oxygen and acetylene, one in each, two separate bottles. You mix them together, you combust them, and you get a really tight focused flame of about 3,000 degrees. There is a bit of finesse, because when you look at the tip of your torch, you get a little tiny blue cone in the middle, bright blue cone. You've then got a darker blue cone, and then you've got other sort of colour flames coming out of it. And one of the ways you need to tune your oxy torch when you're starting to weld is you want this to have a nice crisp edge, no, really sharply defined, but still be a cone or a conical sort of shape. If you end up, and this might erase too much, yep, it did. If you end up with your centre cone looking like that, you've probably got too much oxygen in the mix, and that's going to cause problems depending on what you're welding. If instead of being that sort of more conical shape, it might look a little bit fluffy. I don't know how better to describe it around the outside. And that basically means you don't have enough oxygen. You've got a carburizing flame, which if you're welding something that's sensitive to the carbon, well, you're putting carbon into the joint, and so you'll change the properties. Let's get rid of that guy. The combustion gases create a bit of a loose shield. So if you look in this little image here, in this area where this burnt fuel and oxyacetylene gas is, it's an oxygen deficient environment. So the steel that is molten underneath that isn't going to oxidize. If you had a look on the other side of this, you will get more oxidation and scaling because you're not protecting the underside of that joint. So it's wrong to say it isn't a shielded weld. There is a shield, it's just a very loose shield from the actual torch itself. There's a few things to note with this, and this is two pieces basically making like an angle. First is they've tacked the far end of this corner to try and keep it together. Because as we pour heat into this thing, now you can see because of these colours down here, the heat flowing away from the joint, and it's also flowing in front of the joint, so we're getting preheat as we go along. But metal has a thermal expansion, so as I heat that up, it's going to try and move. So if I didn't put this anchor tack, by the time I got to where they are now, that end is going to be all over the place. And so whenever you're setting a joint up to weld, you tend to tack it in a few different places, depending on the size of the joint, to hold it together whilst you get the main weld in place. Now, there's no evident here filler wire. You'll often see images where there'll be a piece of filler wire and somebody's hand hanging onto it, feeding it into the weld. So you don't always need filler wire. If you've got a joint that's prepped appropriately, and in this case it might be that you've got a joint that looks like this, then if I can put the heat in, then what will happen is this will sort of melt over and it'll end up as a joint like that. So it's a fillerless joint. The advantage of that is that as long as both pieces of metal are cut from the same sheet or whatever, then my joint will be metallurgically identical. If I start using filler rod, I've got a dissimilar metal, so you get corrosion issues and all sorts of things. It's not a huge thing, but it's just a little thing to be thinking about. One of the things, if you're using fillerless welding, or be it oxy or TIG, are the two common ones, or the only ones that you can do fillerless welding with, you can't easily do what's called a cold start, because I need to get enough heat into that corner to melt the job before I can even start moving along. So, I might need to warm it up a little bit before I go, but normally when you start your weld, it takes a fair bit of time to get the first part of it welded, and then once you start running along, it reaches a more reasonable speed. I mentioned brazing on the last slide, and so gas torch is what you would normally use for brazing. The advantage is it's a lot lower temperature compared to welding. So if you've got a big heavy section that you need to join, brazing takes a lot less heat into the joint, so it happens at a lower temperature. Welding thick sections with oxys becomes impossible. It's in part why you see big bridge structures are all riveted together, because there's no way you could oxy weld, two bits of 12mm plate together sensibly. Not saying you can't do it, it's just not sensible. The other thing is the melting temperature of whatever your brazing material is impacts your gas choice. So if you're, and again, you've done soldering. Solder is a 60-40 lead tin alloy. It has a very low melting temperature, so an electric iron, soldering iron, is all you need to do it. So again, different metals, different behaviours, different factors. So I mentioned TIG. Many of you will have heard the term at least, and TIG is tungsten with an inert gas. So what we've got is, here you can see the tip of the tungsten electrode pointing out. This thing around the outside is a shield, or it holds or it controls the gas, this inert gas that flows over the weld pool. So without that shield, it's just going to go yucky. You'll get porosity and all sorts of bad things going on. You can see here somebody's hand holding a filler rod. Filler rod's this guy here. And so you're using the arc, an electric arc that's formed from the tungsten tip in the job to melt the metal, and you progressively add filler material. TIG is a fairly high-skilled process. You've got to keep a fairly constant distance of the tungsten away from the job, and try and not touch the job, because if you will, you contaminate your tip and you've got to stop. If you take your tip too far away from the job, the arc will go out. And that's probably one of the nice things with oxyacetylene welding is if you've got too much heat going into the job, you can pull the torch back quite a long way, and you've still got a bit of a shield around it. You can weld aluminium or steel or stainless with a TIG, but you do need AC for aluminium. And the idea with the AC in the aluminium, you've got this sort of a waveform. One half of this is pulling oxide off the job. The other half is helping you to deposit metal. Aluminium's got a very adherent oxide layer, so you need the AC for it to do it. And they're getting very flash with all sorts of manipulations they're doing these days. So again, the filler wire is manually added. And, you know, a TIG weld done well is a thing of beauty. Whoever did this TIG weld is showing off. The regularity and repeatability of that weave is almost perfect. So they've basically done weaving across the joint with a torch, and at metronome accuracy, you know, the tick-tock that you hear musicians using, with metronome accuracy, they're dipping their rod to add the metal into that weld pool. So that is a really nice looking weld, and you know, it's sort of the pretty welds that everyone likes to show off is their TIG welds. MIG welding, this is really a nice easy thing for most people to get the hang of. MIG has a constant wire feed. There's a wire that's running through this down here. There's a contact tip in this area down here where the electricity connects to the wire and melts it into the job, and the job's obviously earthed. Similar to TIG, there is a gas shield that's blowing around that all the time. TIG is pretty limited. You need to use pretty much pure argon. With MIG, there's a whole heap of different gases, whether you want deep penetration or sheet metal or, you know, range of different optimized gases. If you're MIG welding aluminium, it's pure argon. You don't have any other choice, but yeah, if you're welding steel or stainless, there's a few different options. Obviously, if you're welding a stainless steel, you use a stainless wire. If you're welding a mild steel, you use it's a 70 series wire normally that MIG is using. The nice part about MIG is the torch, you just hold a constant distance from the job, pull the trigger and away you go. Please don't let me make you think it is simple to do a decent weld. There is a reason why qualified welders spend 4 years. And you watch a qualified welder lay down a bead of weld, and the beauty of that weld is amazing. So I've welded plenty, but it's a joy to watch a good welder do it properly. Again, it's a low entry point. You know, you can go down to your local stores and buy a MIG welder for like $500 these days that will do lightweight welding, 130, 140 amps sort of thing. You might hear them talk about gasless MIG, and it's a bit of an oxymoron in some respects. You know, metal with an inert gas. Well, hang on, how can it be gasless? And basically, the wire they use, if you think is, instead of this here being a solid wire, and we're talking wire here that's about 0.8 to, on a big MIG, 1.2 millimeters in diameter. So with a gasless MIG, the wire is actually a thin sheet rolled around, and inside that you have a granular flux. Okay, so when you weld, and this is much the same as when stick welding, which is the next slide, that granular flux breaks down into the weld pool and forms a shield which floats and forms a slag on the top. So it's sort of got all the detriment of a stick weld in that you got the slag, etc. But you don't have to worry about the stick being burnt away as you go. So hence I've said it's sort of like effectively a continuous stick weld. So stick welding or manual metallic arc welding, you may or may not have seen this. You've got a dirty great big power supply, and you have this thing here which is called the stick. The stick is just a rod of metal, and around the outside of it, it has a flux. There's a couple of different types of flux. They've got different things in the flux that can react with the metal in the welding rod to create different structures in the welded joint. And probably some of the advantages of a stick welding process is the huge number of different sticks you can buy. You can buy sticks that do almost any job you want to do, there will be a stick for it. Whereas if you're looking at MIG and TIG, the range of consumables is much smaller. So hence this comment here, the range of electrodes is very high. You get a robust shield through the formation of the slag. So one of the downsides with MIG and TIG is the shield is very loose. And so if you've got trying to weld outside and there's a breeze, the shield will get blown away and you'll end up with a rubbish weld. Whereas a stick weld, you can be almost welding in a howling gale and you'll still have a shield over the weld. You do need to take care of your electrodes. They can absorb hydrogen, and they'll talk about needing to do a low hydrogen weld, which impacts the type of material on the outside of the rod, the flux. But you'll also want to keep your low hydrogen welding rods in a hot box to stop them absorbing any atmospheric hydrogen. It does require a bit more of a skill because that stick is getting shorter for every second you're using it. And so you might start off with a 350 millimetre long stick and you burn it down to, say, about a 40 millimetre long stick by the time that you change out. So you need to be mindful to keep, I don't know if I can draw this that well. Here's your joint you're welding. You've got to keep this electrode distance fairly constant. If you're going in and out, you get all sorts of changes in the penetration depth, and to some extent, you get this sort of stuff. You can see that the weld is inconsistent. We've got inclusions, so just bits of rubbish stuck in the weld. So yeah, it's not a real pretty weld, that one. And that's probably because of the operator not doing things quite right. Conversely, that's a beautiful weld. The fillet is beautifully laid. It's it's even, there's consistency along the joint there. At least in this image, I can't see any evidence of a thing called undercut. And so undercut in that case, if I can draw that, right, that's my beater weld. If I had undercut, I might actually have a divot on either side of that where I've not put enough metal in and I've weakened it because that section thickness is now thinned. So there's no evidence of undercut, there's no evidence of slag inclusions. And if you do this right, you touch the slag with a chipping hammer and it pretty much just falls off. I will point out, let's get rid of some of these annotations. here you can see it's a little bit hollow. And so this through here has got, it's lovely and filled. It's just a nice weld. When you get to the end of where you're welding with a stick, and it's sort of the same for a rigging process really, stick probably more so, you need to lift the stick away to stop the arc. And so lifting the stick away means there's not as much filler material in this area. So it's ended up being a little bit hollow. So when we're doing stress analysis, we need to be mindful that perhaps that little bit there isn't going to contribute the same amount of strength as this piece here. And you have the same sort of a problem at the other end where you're starting. You get cold starts and you can deal with that, but yeah, you just need to be mindful that just because you weld for a certain distance doesn't mean that distance is all 100% perfect. Thermite welds are a bit of a rarity, I guess, in that they're used very specifically, and specifically is railway tracks. Basically, you can see there the residuals of a thermite weld where they've welded these two bits of track together, piece one, piece two. So there was originally a gap between those two bits of rail because they can't make rail continuous. And so they make basically a mould that's the shape of the railway track. Right, and that's split down the centre, obviously. And so that's what this mud is. You can see here where they've stuck the two bits of moulding together around that joint. It's obviously got a hole in the top to let metal run into that gap. The thermite itself is a mix of aluminium powder and iron powder. I think they use a magnesium fuse to set it off. And the thermite metal reacts and it's very, very energetic and it melts the iron. And then at the bottom there's a plug that falls out, I think. And that metal then runs into the die and fills the gap. Before they set off the thermite, if you see this happening at night on a railway, which is the only place you'll see it, they'll have a huge oxyacetylene torch warming the rails up to get it nice and warm so that it doesn't quench the weld metal too quickly and cause metallurgical issues. So you might see a big glow from some oxyacetylene torches as they warm the rails. They'll have the moulds ready to go. These are just sand, basically. They'll slap those on, mud them into position, light the thermite and stand back, and it'll dump its load into there. They knock the moulds off just with a hammer. They're disposable. And then they try and clean off excess metal before it gets too hard. And then eventually they go over that with a grinder just to finish that welding process off or finish the joint off. So for a very long time, pretty much everything was thermite welds. There are railway tracks I know a process called flash butt welding, where I'm going to talk a little bit about spot welding. I won't talk much about flash butts, but you can imagine if big machine grabbing these two rails, putting an enormous amount of current through them until it forms an arc, and then you pull them apart a little bit, get it really, really hot, and then you whack them together and form a butt weld. Yeah, it's pretty impressive, that technology. Okay, plug and slot welding, just drill a hole through the top piece, and that allows you to weld around that circle to form your plug weld. So here, if you look here, I could weld along there, I could weld along there, but I don't have anything in the middle of it. So plug welds are a way to get more connection, if you like. Slot, well, you just machine a slot out. It's the same thing. I've probably already used some of these words, but a butt weld is where we've got two pieces of plate butted together. We use a fillet weld anywhere where we're going to fill something up. that's a fillet. So we can do a lap joint where we've got 2 fillets, a T-joint, this is fairly common, 2 joints. This would be a fillet weld along here. The edge joint, yeah, I guess you'd call it a fillet, but it's just sealing that joint off. We also talk about stitch welding, and you might have a symbol that looks like this. I'm going to put a 6mm fillet weld, and I'm going to have a 50-100. And so that means I'm going to weld for 50mm and leave a gap of 100mm. And so that's what we talk about when we're talking about a stitch welded joint. And the advantage of that is that if a crack starts to propagate along the joint, it runs into an air gap and it can't continue propagation. So it's useful for that sort of stuff. It also means there's less weld metal, less process, less distortion, a whole heap of different good reasons to stitch weld. For completeness, spot welding. This is just a handheld spot welder. It's normally used with sheet metal. You put your 2 pieces in, clamp the handle down, and normally there's a switch that's automated when you close the handle. So you got the pressure of the joint, you put a heap of power through it, it melts, and it joins the metal together. That pressure and temperature, it just joins it together. Where you will often see these large scale is, on the end of robotic arms doing car body manufacturing, sheet metal stuff. So the robots are really good for that sort of thing. There's also a thing called a mash weld, which is a similar sort of process, except you might have 2 wheels, and the joint, your 2 pieces of sheet metal feed through there, and you pulse. Similar to the same sort of process you do with an ordinary spot welder, get it hot enough for it to self-fuse. You can sort of see here that there is a zone of influence. So there might have been, this is my contact point, but I then end up with an area out here that's actually fused. So if I then come back through and put a second spot weld here, I will get a continuous weld, if you like. So if I do this with rollers, right, then I can just seam it through and it's done, basically. Again, really for completeness, forge welding, as I said, if you get something hot enough and squish it together, it'll stick. So knife and swords people have been doing this for decades or millennia. So what you're looking at here is a stack of metal, right, that's been tack welded along the edges just to hold it together in the forge, heat it up until it's the right sort of forging temperature, and then you give it a very large hug. You can do it with a big hammer or a press. And it was called forge welding, fire welding, hammer welding, a whole heap of different things. And where you'll often see it today, a plug for a show I don't mind, Forged in Fire, they're forever doing Damascus steel. And that's the other thing you might hear is Damascus. Damascus steel is really just layers and layers of steel squished together. And if they're slightly different in their composition, you can etch it using ferric chloride and you get these patterns. Now, how you get different patterns, there's 1,000,001 different ways you can do this. But if you ever want to see a bit of forge welding, there's always people on Forged in Fire trying to do stuff that they probably shouldn't be. But it's interesting to watch the process. The final one I want to talk about is just friction welding. So here we've got 2 bits of metal. We're spinning them either in opposite directions, or one's held still and the other's spinning. So if we push those together, differential velocity equals heat. We get it hot and then we squish it together. We've done a friction weld. Now the advantage here is, of course, we know it's got full penetration. We don't introduce any sort of filler material, so we have control over the composition, etc., etc. So all of those are useful things.